Hello, everybody. This is Mrs. Rainbow, and I am here today to talk to you about 2.06, the periodic table. All right, let's get going. So, what we've been talking about is we've been talking about the arrangement of the the arrangement of the electrons in an atom. So far we've talked about how matter, oh, this is so fun, so you can like watch this as I'm doing this. So far we've talked about how matter is made up of atoms and how an atom consists of a nucleus, which has protons and neutrons in it, and then it has electrons around the outside. And what we discussed very extensively in the last section is where the electrons are located in these shells around the outside of the nucleus, and how it's really not, we really don't know exactly where the electrons are. We just know the probability of where they might be located within a shell, and we call that electron clouds, or where their orbitals are. So now what we're going to do is we're going to take a step back and we are going to start looking at the periodic table. So now we know the basic information about the structure of an atom. Now we're going to look at, okay, how are they organized on a periodic table? The periodic table is the most awesome thing ever, and I love my periodic table, and hopefully you will start loving your periodic table by the end of this. Maybe you'll like carry it with you wherever you go because you might need it. So the first thing to discuss is where it all came from, and Mendeleev was the guy who created the periodic table. And when he created the periodic, he looks pretty intense here, kind of hairy. In creating the periodic table, basically what he did, he arranged the elements in order of increasing atomic mass. So he was able to weigh elements and figure out their atomic mass, and he figured out how to organize them according to their increasing atomic mass. And from that, he noticed that there were certain chemical properties that tended to show up like as a trend. And as a result of that, he could predict the properties of certain elements based off of what he has organized, okay? And from this, he came up with the periodic table. And this is like isn't that cool? Look at that. That's the language. So anyway, this is the original periodic table. And so if we look at the word periodic means like, periodically I go running. That's like never, but okay. But like periodic table, periodic trends is what that's what it stands for. So anyway, this is the beginning of the periodic table. And from this, what he decided is he put the elements into two basic groups. And the two basic groups that he came up with were metals and nonmetals. And metals are metals. And so they're like good conductors of electricity and heat. They are typically a solid at room temperature. So we always talk about states of matter. Okay, so at room temperature, they're a solid. They're malleable, which means that they can be like hammered out. They're flexible. They're ductile. Ductile means that they can be drawn into a wire. They're shiny, also known as lustrous, and they have a high density, okay, a higher density. You could use the word lustrous when you're talking about like, oh my God, my face is so lustrous. Shiny, get it? All right, never mind. Non-metals. So non-metals are they're non-metals. They're not like metals. So they're poor conductors of electricity and heat. They are typically a solid, liquid, or a gas at room temperature, so they can be any of the three states. And they are typically brittle and break easily. They are not shiny, they're dull, and they have a lower density. So you can see it's like opposites here, right? So those were the two basic categories. And then we came up with a third, like in the middle category, because you always have those weird ones in the middle that are just in the middle, right? They just kind of go both ways, and that's the metalloids. And the metalloids are elements with characteristics of both metals and nonmetals. Isn't this picture cool? PowerPoint just suggested it to me. I'm like, ooh, that's like a cool way of being like metalloids. Metalloids. I always think of Metallica. So this is a picture of the three different types of elements or groups of elements we could have. So you have your metals, you have your non-metals, and you have your metalloids here. And I like this picture because it gives you examples. Like it shows you little pictures of what they look like, you know, and like, look, that's a non-metal right there. And then this is metalloids. Look at them. Aren't they cute? And this gives like the same definitions that we just gave. So, you know, this might be something to write down. I'm not going to go over it because we kind of already did go over it. But those are characteristics for you, so you can write that down and realize that the PowerPoint is also linked underneath the video, so you can just go and look at it and either save it or write it down. But those are the three groups of elements, or how we organize our elements, either metals, metalloids, or nonmetals. The majority of your elements on the periodic table are metals. So now we're going to get into how is the periodic table organized today? And this is a beautiful picture of a periodic table. This is a big one. I know these. I had one of these in my classroom. They're huge. They're beautiful. And let's get into it. Let's delve into our relationship that we are now going to develop with our periodic table. If you don't have a periodic table, there is a periodic table on my homepage. So you can download that periodic table and keep it somewhere safe in your computer or print it out and laminate it or something. But you should always have a periodic table on you from here on out because we're going to be using those babies. We'll be using them and you need to have it. So here we have the periodic table, and it is in order of increasing atomic number, which I'll talk about in a second. But if you look, you can see that we have it divided into the metals, the metalloids, and the nonmetals. And so you can see the majority of the periodic table is blue because the majority of our elements are metals. And then we have this little fooky pooky poo section right here. These are the metalloids. And if you notice, there's like these two different colors here because they're kind of weird. They're kind of different from the rest of them. And then you can see we don't have very many nonmetals, but there are these, and then hydrogen is over here. And there's a reason for that, but just for now, just understand that hydrogen is a metal, but we put it over here. Hydrogen is a nonmetal, but we just put it over here by the metals. It has to do with its number of electrons, okay? But everything else, if you can see here, this is all metals, okay? Now, don't you wish it was that easy? But it's not that easy. We have to go further. So when we talk about the periodic table, we have names that we use for the columns and for the rows. We don't say columns and rows. For the columns, we call them groups. And for the rows, we call them periods. So this is a great way to remember it. If you're not looking right now, look at me. I'm going group, period. That's how I remember it. Get it? Group, up and down, period. Get it? Yeah? Okay, so I love doing that. So every time I'm like talking, I'm like group, period. Okay, group. So groups are the columns and periods are the rows. Another word that your lesson talked about is we also call groups families. I'm never going to call it a family. I like saying groups because I remember group, period. And it's just like family, period. It just doesn't feel as right as saying group. So I'll be usually using group. But if you see family, it means the same thing as group. You can see it's nicely rainbow colored there, which is nice. Okay. So the periodic table is organized, and we have different groups are labeled. They have names to them, and different periods have names to them. So if you look here, I'm just going to kind of show you. We're just kind of going to go through this and just look at it. So first of all, if you notice, each group is numbered. So we have 1, 2, 3. Actually, I'm going to use the highlighter. Hold on. Let me get my highlighter on. Okay, so you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we label the groups, okay? Now, depending on the periodic table that you get, your periodic table has it numbered this way. But there are also old school periodic tables, like old school, meaning back in my time. And when we used to do this, we actually separated them into A and B categories. So if you're looking on the internet for a periodic table, let's say you're having a DBA with me and you forgot your periodic table, so you just come up with one really quickly, you might get confused by seeing this, so I just want to go over it with you. So if you look at other periodic tables, the groups might be labeled this way. This might be 1 Why isn't it? It's not. Okay, let's try typing it then. Let's see if we can type it there. 1, that's I, 1A. So that one's 1A, okay? And we call this one 2A, okay? And then these ones here, these are group B, 1 through 10. So this is another way of numbering it. So we would call this one right here, instead of 3B, 1B, 2B, 3B, 4B, 5B, 6B, 7B, 8B, 9B, 10B. This is another way that they number the groups. I'm sorry that we have two different ways of doing it, but it's important for you just to kind of see. And then instead of 13A, 13 here, it says 3A, get it? So it's like the transition metals are the B's and the transition metals are the B's and the rest of it are the A's. And then this is 4A, okay? And then we have, this one is 5, that's a percentage sign, 5A, okay? Then 6A, move it over, okay, 7A, and then 8A. Okay, so these are the two ways that we number the groups. You're going to see it more like the way that is on your periodic table. So the way you'll see it is you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's probably going to be the way you see the groups. But you might find a periodic table that would separate the middle as B and the two ends as A. So instead of, 3 here, it's 1B. So just be aware of that, okay? So we have names for the different groups. So our group 1A here, they are the alkali metals, okay? And if you notice, we talked about how hydrogen is here and how it's not really a metal, but for some reason it's there. So hydrogen is not an alkali metal, but it does have properties of alkali metals, but it's not a non-metal. But it's not a metal, it's a non-metal. So please realize that hydrogen is there because it has similar properties to alkali metals, but it's not a metal. Then we move to the next group, and the next group is the alkaline earth metals. That's group 2. And then the transition metals are groups 3 to 12. So these are your transition metals here. Within your transition metals, you have the lanthanide series and you have the actinide series. And these guys go in right here, okay? So it's like too long to shove these in here and make the periodic table too long. So they just put them down here, and that's what those little asterisks are for. From there, it gets a little wonky. So if you remember, we talked about how the metalloids, so these are the metalloids right here, nicely color-coded, okay? And if you remember, it said that this was kind of, these two here are kind of can be questionable, but on the periodic table on your, in your lesson, it made these the post-transition metals right here. They have their own characteristics, and that's group 3, 4, 5, and 6. But if you notice, it's not all of group 3, 4, 5, and 6. So some of them are metalloids. These are just normal non-metals right here. And then group 7 is the halogens, and group 8 is the noble gases, or 18. Group 17 is the halogens, and group 18 is the noble gases. You have to bear with me because I'm really used to using the 1A and 1B system. Okay, so this is how the periodic table is organized. This might be helpful for you to have. This might be something that you might want to print out so you have it so you know where everything is located, okay? Now, this is all the characteristics of them, and you are going to have questions asked to you on your exams about the characteristics of them. We're really not going to go into them because, I guess I could just kind of say a little bit about them. The alkali metals are the most reactive. They're extremely reactive. Like, they cannot be alone. They have to so they are usually bonded to something else. It's very difficult to keep them not reacting. These are really interesting they are very sensitive to things. And then you have group 2A, which is the alkaline earth metals. They are still reactive, but not as reactive as group 1A, but they're still so reactive that they're typically not found alone. And they're harder and denser than the alkali metals. Then I'm going over to the other side of the periodic table, which is the halogens. This is your nonmetals. They also have a high reactivity, and they go through phase changes at room temperature. That would be like chlorine, okay? Then you have your noble gases, and these are unreactive nonmetal gases. They don't react with anybody. And your noble gases are your like neon, like if you ever seen neon signs, right? And they like make that glowing color to them, that's a noble gas. They're unreactive. And when you heat them up, they make a pretty cool color. Transition metals are in the middle, like we said. The thing about them is they have multiple ions. We'll talk more about that later. They're harder than the other metals, but they're less reactive. Okay, they can exist alone. So this would be like copper, right, and iron. Like those guys you can have on their own. They're not as reactive. They can react. Sometimes when you're wearing them, they do react with your skin. But they don't react as much as, say, sodium does. Sodium is very reactive. Post-transition metals are those ones in like group 14 on, and it's kind of like below the metalloids. They are opaque solids with higher densities, and they don't conduct heat and electricity as easily as other metals. Then you have your metalloids, which is that funky little green section, and they have properties of both metals and nonmetals. They're things like semiconductors, like silicon. Some can conduct electricity and some don't. Some are conductors. So they have characteristics of both metals and nonmetals. And then just so you know, the lanthanide and the actinide series, so both of these are part of the transition metals, okay? Lanthanide are soft, rare earth metals. They are very difficult to extract from the environment. They're known for their silvery color, and they're used in the production of glass and laser technology, which is kind of cool. The actinide series is even cooler because they're human-made. They do not occur in nature. We've actually created them, like, or they're human-made. They are usually silver white luster in their metallic form, and they are radioactive, which means they can cause cancer. Bum, ba-da-dum, bum. That's bad. All right. So the next thing that we need to talk about is how do you figure out what element you're looking at? And all elements are defined by their number of protons. So no two elements have the same number of protons. The number of protons stays the same, and that is how we identify an element. We identify an element by its number of protons, okay? So now we know the arrangement of the periodic table. We know we have these different groups and periods, right? And we know that there are different characteristics within them, between the metals and the nonmetals and metalloids, and the different groups within the metals and within the nonmetals. Now what we're going to do is we're going to talk about, okay, let's talk about the individual elements that you find on the periodic table. And what you can find on a periodic table is you find this little picture here, okay? And on this picture right here, what you see is you see a symbol. And that chemical symbol is the shorthand symbol of the element. Just so we know, potassium, everybody thinks potassium is P because we're saying potassium, but it's not. Potassium, P, is actually phosphorus, okay? Potassium is K. I know, it's crazy. And that's some of the things you see. I mean, look at this one. AU is for gold. It's because some of their names come from, some of their symbols come from their Latin root. Because that's what this is based in. So this is gold, so this is its chemical symbol. And then you see that there are two numbers up here. There's one with a decimal place, and there's one that's a whole number. The one that's with the decimal place, actually, I think I'll type it in. The one with the decimal place, this number right here is the atomic mass, okay? And then this number right here, this number that does not have the decimal is the atomic number. It's really easy to get these two suckers confused. So you want to make sure that you see here that the one that has the decimal place with it is the atomic mass. The whole number is the atomic number. So the atomic number is one of the main ones that we like to talk about because the atomic number tells you the number of protons in an element. So this means that gold has 79 protons in it. Now, the atomic number tells you the number of protons. The number of protons is always equal to the number of electrons. So that means that this gold right here has 79 protons and has 79 electrons. And we know that instantly just by looking at the atomic number. What about the number of neutrons? Don't worry about it, we'll get there. Now, the atomic mass is the average masses of all the isotopes of the element. We're going to talk about isotopes in the next slide, but basically most of your mass of your element comes from the nucleus, and it comes from the arrangement of the neutrons and the protons together, okay? So this is what we're going to be talking about on the next slide. All right, so we're clear with this information. Atomic number is the number that doesn't have the decimal place. It's the number of protons and the number of electrons. The number with the decimal is the atomic mass, which is the average mass of the isotope. So you're wondering, what is an isotope? All right, so your lesson doesn't really clarify this very well. So an isotope is basically all elements have they have the same, all elements have isotopes. And an isotope is basically an element where you have elements that have the same number of protons but different number of neutrons, okay? Okay, so each element has a couple of different isotopes, and an isotope has the same number of protons and different number of neutrons. How do we find out the number of neutrons in an element? We look at the mass number, okay? We look at the mass number. The mass number is not found on the periodic table. The mass number is not found on the periodic table. What the mass number represents is it represents the number of protons plus the number of neutrons in an element. So there's two different ways that you'll see the mass number. You'll see it like this. Well, it says chlorine 35. This 35 here is the mass number. It's the number of protons plus the number of neutrons for that element. Or you'll see it like this. This is a really nice way of seeing it because the mass number is on top and the atomic number is on the bottom. So if we were looking at this isotope of chlorine, what we would see is that the mass number is 35 and the atomic number is 17. So if the atomic number is 17, that means that this element has 17 protons and 17 electrons. Because if you remember, back in the previous slide, we said that the atomic number tells you the number of protons and the number of electrons in an element. So this element has 17 This element has 17 protons and 17 electrons. Am I even recording? I am recording. I had a brain fart. Okay, so now to find out the number of neutrons, I don't see it. Oh, it is recording. Okay, so to find out the number of neutrons, the mass number is the protons plus the neutrons. Okay, so you look at your mass number, and your mass number is 35. And you know that you have 17 protons because it tells you in the atomic number. And then you're trying to figure out the number of neutrons. So you do 35 minus 17, and that gives you 52. So this element here has 52 neutrons. So this element of chlorine right here has 17 protons, 17 electrons, and 52 neutrons. And we know that from these two numbers here. You have to have the atomic number and the mass number to find the number of protons, neutrons, and electrons in an element. And this picture right here is showing you an example of isotopes. So carbon has 3 isotopes to it, carbon 12, carbon 13, and carbon 14. And if you remember, these numbers here represent the mass number. Okay? Now, the atomic number for carbon, and you find this on the periodic table. So if we look on the periodic table, and we look to where carbon is, which carbon is right there, okay, carbon has the atomic number 6. So that means carbon has an atomic number of 6. So that means it has 6 protons. Each one of these isotopes here has 6 protons and 6 electrons. That doesn't change. So the only thing that changes here, if you notice, is the number of neutrons. In carbon 12, that 12 is 6 plus 6. So there's 6 neutrons, 6 protons. In carbon 13, 7 neutrons, 6 protons. Carbon 14, 8 neutrons and 6 protons. Ooh, it says protons. It's nice to know when other people are making mistakes, not just me. Like, oh my god, am I recording? Okay, so now let's apply this. No, I don't have the answers to this. I have to like do it on the fly. All right, so let's apply this. You have to use a periodic table. Okay, so if you can get the periodic table on my homepage. So pause, open up my homepage, download the periodic table, have that bad boy with you. Okay. All right, so the first question is, what are the number of protons, neutrons, and electrons in a neutral atom of oxygen? Okay, so we look on the periodic table, and we find oxygen right here, okay? And if you notice, oxygen has an atomic number of 8, okay? So this is a neutral atom, which means they're all equal. So if it has an atomic number of 8, that means it has 8 electrons, 8 protons, and 8 neutrons. Okay? Now, that's the first one. That one was easy. So easy. What is the name of the element with the atomic number 29? So, you can pause, but I'm going to go. I'm going to look on the periodic table. I'm going to look for the number 29. Oh, I see it right there. So, what is 29? It's Cu, miss. It's Cu. Cu stands for copper. So that is copper. Cu. If you were in real school, I'd make you memorize all the element symbols, but we're not in real school. We're in virtual school, so you don't have to memorize them, which is really nice. But you should know them. Which element has an atomic mass of 87.62? Okay, so we'll go and look around the periodic table and try and find one that has close to the atomic number 87. I don't even know where that is. 87.6. So we would look at the bottom numbers here. Okay, so I'm going to look at it because I can't see that upside down. Oh, I see it. Okay, so you see that right there? See how it says 87.62? And it says SR? That's strontium. So this one is strontium. Okay. If fluorine has 9 protons and 10 neutrons, what is the atom's atomic number and mass number? Okay, so the atomic number, if you remember, is the number of protons. So that means that the atomic number of fluorine is 9. And the mass number, if you remember, the mass number is the number of protons plus the number of neutrons. So what you would do is you'd add you'd add 9 plus 10, and so the mass number is 19. So for this element of fluorine, or this isotope of fluorine, it has an atomic number of 9 and a mass number of 19. Okay? Okay, next one. What are the number of protons, neutrons, and electrons in U-256? So this is uranium. Uranium is radioactive, and it's really cool. So let me find uranium on the periodic table. Bloop, 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 bloop. Come on, where are you, boo-boo? Where are you, boo-boo? There you are. You're down here. See uranium? It's down in the actinide series. So you can see that its atomic number, it's the U. So its atomic number is 92. So uranium's atomic number is 92. So what that means is that means it has 92 protons and 92 electrons. So easy. Now, this number right here is the mass number. So now what we do is we take 256, and we know that the mass number is equal to the number of protons plus the number of neutrons. We know the number of protons from the atomic number. So it's 92 minus x. So then what you have to, 92 plus x. And then what you do is you do 256 minus 92, and boom, you get 164 neutrons. So for uranium-256, it has 164 neutrons, 92 protons, and 92 electrons. So you need your periodic table to figure these out. And then what is the chemical formula for potassium? Just because I see that so much, I just want to get it out there now. Look, there it is. Look, it's a K. Potassium. K, not P. That's just a personal pet peeve. Get it? All right. Oh my God. More practice. Oh Lord, this is awful. How come I have so much practice on here? All right. Well, okay, let's do it. We'll do like 2 more. I'm not going to do all of these. All right. I should just do them all so you have them so you can practice them. All right. I'm just going to give you the answers to these and then we'll do this one first. Okay. So you have chlorine 37. Okay. Chlorine 37. So it's telling you this is the mass number right here. That's the mass number. You have to look on the periodic table to find the atomic number for chlorine. And the atomic number for chlorine is 17. So the atomic number for chlorine is 17. That means that chlorine has 17 protons, 17 electrons, and then what we do is we take this 37, that's the mass number. So 37 equals 17 plus the neutrons, remember, because the mass number is equal to the number of protons plus the number of neutrons, and the atomic number is equal to the number of protons, and it also is equal to the number of electrons. Okay, so then you take 37 minus 17 and you get 20. So you have 20 neutrons. Okay, I think I'm going to stop right there and I'm not going to do any more. I think that's enough. I think I was way over ambitious with this, and yeah, we're just going to move on. If you want the answers to those other ones, I'll send them to you. Just text me because we have more to learn. All right. So you might be wondering, well, what's the point of the atomic mass if you got this mass number here? Well, the mass number is not on the periodic table, okay? But the atomic mass is, it's that decimal number. And so the atomic mass is the average of the isotopes of the element. So like I said, every element has a couple of different isotopes of them. And if you remember, isotopes, if we want to just remember what an isotope is, an isotope, they all have the same number of protons, but the number of neutrons differ. And neutrons play a very big role in mass. If you remember uranium, I don't know if you remembered in uranium, but they had a lot of neutrons in them. And that's why uranium is a very big nucleus, comparatively speaking. It's very heavy because it has a lot of protons and it has a lot more neutrons to it. So in an isotope, they have the same number of protons, but the number of neutrons differ. So all elements have a couple different isotopes. When we determine the atomic mass, what we do is we look at the percent abundance of each isotope in nature. So let's say we have carbon-12 and carbon-13. So carbon-12's abundance is 99%. So 99% of carbon is carbon-12. And then 1% of carbon is carbon-13. So then what we do is we take the mass of that isotope. So the mass of carbon-12 is 12. The mass of carbon-13 is 13. We multiply it by its percent abundance. Then we add those two numbers together, and that gives you your average atomic weight or atomic mass. This is the same thing as saying atomic mass, okay? So the atomic mass is an average of the isotopes, okay? That's basically what it is. So an atomic mass is the average of the isotopes, which is why it has a decimal place there. It's because it's an average of it. All right. Oh, that's it. That's all I had to do. I guess we could have done those other, I don't want to do those other problems. I'm sorry. I'll text me if you want to do them and we can do them together. We'll have fun. This is a really cool lab. It's called Penny Isotopes. This is not a required lab. This is a try-at-home activity. And this is just to help you understand isotopes better. This is actually like to help you understand how we determine atomic mass. And so it's like a percent abundance of like pennies, and it's by the dates. We do this lab in school, actually. This is one of the labs that we actually do in school. And it's I don't know if kids like it, but I like it. But I'm a nerd, so like, you know, I like chemistry. So, you know, if you want to do it with your family, your brothers and sisters. Collect all the pennies. That's it. So, from this lesson, you should be able to answer the following questions. What is the early history of the periodic table? Mendeleev. And he organized it according to increasing atomic mass. What categories of elements exist based on similar properties? That would be metals, nonmetals, and metalloids. What does the periodic table tell us about an element's mass and subatomic particles? Okay, well, the atomic number tells you the number of protons, and it also tells you the number of electrons. The atomic mass tells you the average of weight of the percent abundance of the different types of isotopes of that element. How do the mass and number of subatomic particles differ in an isotope? It differs by the number of neutrons. And how do scientists calculate the average atomic mass of an isotope? By multiplying by percent abundance. Okay. So these are the basic questions that they are things that they want you to know. I hope this was helpful, and probably should redo this again and do those other questions, but I don't want to. So that's it. I hope you're having a great day. Thank you very much. Bye-bye.